In this problem, we have two rate constants measured at two different temperatures. We can write the Arrhenius equation for each of these two experiments. Start with K1, so the ln of K1. This would be the rate constant measured at the temperature T1. And then we can write the analogous Arrhenius equation for the ln of K2. That would be the rate constant measured at the temperature T2. Now, in each of these expressions, there are some common terms. First of all, the ln of A, ln of the frequency factor, would be the same in both terms, and the EA would be the same in both terms. Those are not going to change even if the temperature is changed. To simplify these two expressions, we can subtract one from the other, so ln of K1 minus ln of K2. That gets rid of the ln of the frequency factor immediately. We pull out the remaining common terms, minus EA over R, and then we have an expression with the two temperatures, T1 and T2. We will rearrange this to put the EA on the left side. That's the value that we're after. And so we have a whole expression now for EA involving K1, K2, and T1 and T2. Be careful when you're entering these values into your calculator. It's difficult to get it right all of the time. The number you should come up with is 65 kilojoules per mole, and those units come from the gas constant, the R value. In the second problem, we have a number of experiments that have been done, and therefore a number of rate constants collected at different temperatures. Once we have more data, what we can do is we can plot this data. From the slope, we get a more accurate evaluation of EA. Start with the Arrhenius equation again to see exactly what we want to plot. Ln K is equal to ln A minus EA over RT. So on our y-axis, we're going to plot ln K. That's our dependent variable. And what we're changing, so what we would plot on the x-axis, would be 1 over T, 1 over the temperature. In such a plot, the slope would be equal to minus EA over R. So here's the numerical data we've calculated, our ln Ks and our 1 over T. When we plot these, we get a linear plot. The slope of that plot would be minus EA over R. Therefore, EA would be equal to the slope, and that comes out of a linear fit in Excel, 51.1 times 10 to the 3 degrees Kelvin, multiplied by the gas constant, the R value. And therefore, the answer for EA is 425 kilojoules per mole. Watch those units again, they come from the R value.